Optional, Part 3.5, The Mathematics of Magnetic Resonance. Here's the formula for the torque on a planar current loop in a uniform magnetic field. Previously in Part 3 we explained its overall context within the story of magnetic resonance, which is that this formula demonstrates how there is an electromagnetic torque force on an electron or proton to allow it to undergo gyroscopic precession in the absence of gravity. However, the previous explanation of the origin of this electromagnetic torque force was very incomplete and hand-wavy, so to say, and we are still missing out on the mathematical details of exactly where this idea even comes from in the first place, and we are missing insight to the key question. According to mathematical electromagnetic theory, how do these electromagnetic torque forces fundamentally arise, and how do we mathematically quantify their direction/orientation and strength? Because we provided this cross-product formula for the torque on a current loop in a uniform magnetic field without a solid mathematical proof or derivation, this is the missing hole that Part 3.5, the Mathematics of Magnetic Resonance, will aim to more rigorously cover. This section is optional because it is very mathematically intense compared to the other parts of the series, and without some basic amount of familiarity with multivariable or vector calculus, while delving so deep into the math, one might get so bogged down by the fine minute details of the trees and lose sight of the big picture of the forest, so to speak. If one has no background in multivariable calculus, perhaps it is still worth following along and trying to grasp the big picture roadmap of the mathematical logic, and perhaps some of the key concepts from the field may sink in, and perhaps by simply just looking at the visuals and focusing on the geometry of the diagrams instead of the equations. That being said, math is a very interesting field, and some viewers might find this section particularly interesting and insightful, which is why it is still worth including as an optional component of the video series. So magnetic resonance has the word magnetic in it, so let's start from fundamental concepts of electromagnetism. So here we have the Lorentz force law equation. Let's assume there's no electric field present, so we can ignore the first term and focus on the second term. What does this equation mean? It means that a charged particle moving in an external magnetic field will experience a force that is the cross product of the velocity vector and the magnetic field vector scaled by the charge of the particle. That means the experienced force vector will be simultaneously both perpendicular to the direction of movement and also perpendicular to the orientation of the external magnetic field, both of which are confined to some plane. As an example, from the diagram, the charged particle is moving to the right, the magnetic field is pointing up, and so the force on the particle will point out of the screen or page towards the viewer. So in the previous example, we had a moving charge in an external magnetic field. And what are moving charges? That is electric current. Let's examine the cross product's first term's units in more depth. Q is coulombs, V is meters per second. That means that every second we have a certain amount of coulombic charge moving a certain distance in meters. Let's keep that in mind for a bit. Now let's say we have a straight line conducting wire with uniform current flowing through it. That means every point along the wire has the same amount of electric current going through it. So if we look closely at any particular point on the wire, intuitively there is the same amount of charge passing through that point of interest every second. Because current has units of coulombs per second, it is the same no matter where we look on the wire. Now of course this wire has a certain amount of length. If at every point along the length of the wire there symmetrically happens to be the same certain amount of coulombs passing through any and every particular point every second, the only way for this scenario to happen is if charge is uniformly distributed along the wire and all charge is uniformly moving with the same velocity along the wire. This scenario is analogous to how if electrons were playing musical chairs, but we never removed any chairs, everyone would be uniformly distributed, one person per chair, and simultaneously move with the same speed, so to speak, and everyone would together at the same time just keep switching one chair over to the right to the next neighboring chair. This actually is indeed sort of the inorganic chemistry microscopic picture of electrons and valence bands of how semiconductors and conductors work, and the macroscopic picture of how electrical circuits work. So that means if we look at the wire as a whole, every second a certain amount of coulombic charge passes through the wire whose length is a certain distance measured in meters. In other words, every second a certain amount of coulombic charge passes through a certain distance, the length of the wire. This is exactly equivalent to our previous definition, which I'll repeat from previous. The Lorentz force law's cross-product first term's definition. Every second we have a certain amount of coulombic charge moving a certain distance in meters. That means according to the Lorentz force law, a straight line wire of current inside a uniform magnetic field will experience a force on the wire that is the cross product of the current vector and the magnetic field vector scaled by the length of the wire. And considering any electrical circuit is made up of a bunch of infinitesimally small straight line wires of current chained or connected together in a loop to close the circuit, this will definitely come in handy for real-world applications. As an example, let's look at this situation. Imagine we place in a uniform magnetic field of strength B pointing up a rectangular closed circuit with a horizontal width of A and a vertical length of B with uniform current I going counterclockwise. By the Lorentz force law and right-hand rule of the cross product, the upper horizontal segment of width A will have a force of A times I times B pushing it into the screen away from the viewer, and likewise the lower horizontal segment of width A will also have a force of A times I times B pushing it out of the screen towards the viewer. If we look at the vertical segments of length B, the current is parallel to the magnetic field, so the cross product of the two will be 0, and thus by the Lorentz force law, there will be no force acting on the vertical segments of length B. Now let's draw a free body diagram of the forces acting on the rectangular circuit loop, which we'll assume to be a rigid body so it doesn't bend under their forces. Notice by obvious mechanical intuition, the loop will start to rotate due to the equal but opposite forces applied at different locations some distance apart, which in engineering terms we call a couple. By symmetry, the axis of rotation will be located halfway along the segments of length B, directly in the center. Since the sum of the forces in the object is 0, the current loop will not undergo translational movement, but it will instead spin about the center axis of rotation as a result of the couple, and this is exactly how electric motors work at the fundamental level. Now, when an object undergoes forces that causes it to only rotate and not exhibit translational motion, that is once again what is defined as torque, or in other words, rotational force. Now you can start to see why discussing the gyroscope would come in handy. What is the torque acting on this rectangular loop? Well, we have a force of I times A times B applied at distance B over 2 from the center of rotation, and we have another force causing rotation in the same direction of I times A times B applied at distance B over 2 from the center of rotation. Thus, the total torque will be I times A times B over 2 plus I times A times B over 2 equals I times A times B times B. Notice how the rectangle's area is at A times B, so we can simplify the expression to be I times B times area. But what if our current loop is not actually a rectangle, but instead some arbitrary planar closed current loop? Will the torque induced on the loop still be the same amount, I times B times area of the loop? Will the torque be in the same direction as well? In fact, indeed, yes it is. I will now provide the proof. So let's assume our arbitrary closed current loop is confined to the plane of the screen and that the counterclockwise current is uniform and of strength I throughout the entirety of the loop. The loop does not self-intersect, and the current loop is a rigid body so forces do not alter the shape of the loop. Let's assume the magnetic field B is uniform and points upwards in the plane of the screen so that it is oriented parallel to or inside the plane the loop is confined to. First, let's show that the sum of all forces on the current loop is 0. So that means the loop itself will not exhibit translational movement and will only undergo rotational movement from the rotational torque forces. Due to the geometry of the situation and the right-hand rule from the Lorentz force law, forces on any part of the loop can only point either out of the screen towards the viewer or into the screen away from the viewer, and thus the sum of all forces will end up either pointing in one of those two directions or all canceling out to be 0. Let's assume the up-down pointing magnetic field points in the plus y direction and left to right on the screen is the plus x direction. From the geometry of the Lorentz force law, the amount of force contribution from any particular current loop line element is the projection onto the vector IBI, where I is the unit vector in the x direction. If we integrate over all current loop line elements confined to the xy plane to get the total force acting on any part of the current loop, we get a closed contour line integral over the vector field IBI. IBI is clearly a conservative vector field because it can easily be written as the gradient of the scalar field IBX. By the gradient theorem, or fundamental theorem of multivariable calculus, any closed-loop line integral in a conservative vector field is 0. Alternatively, the curl of this vector field is 0, so by Green's theorem or Stokes' theorem, clearly any closed-loop line integral must be 0. Also note that in this particular case of vector field, this just simplifies down to the fundamental theorem of calculus in one variable or one dimension. All plus x projection contributions cancel out all negative x projection contributions along a closed path that ends up back where it started. Okay, so we've shown that the total force acting on the loop is indeed 0. That means the loop will not exhibit translational motion, but it will rather experience rotational forces and torque, causing it to rotate about some axis of rotation. Now this axis of rotation must exist somewhere, and that means if we know where this axis of rotation is, we can divide the current loop into two distinct regions by chopping it up into two pieces at the axis of rotation as shown in the diagram. Since we hypothetically chopped the loop up into two separate pieces at the unknown but existing axis of rotation by construction of torque-force couples, the total sum of all force times distance moments on one chopped piece of the loop must be equal in magnitude and opposite in direction to the sum of all the force times distance moments on the other piece of the chopped loop. That means if we calculate the total sum of all force times distance moments on one particular side's piece of the chopped loop, we know the total sum of all force times distance moments on the other side's piece of the chopped loop will be equal in magnitude but opposite in direction by symmetry of torque-force couples. So for now, let's just look at one side of the chopped loop. Without loss of generality, we can set our arbitrary coordinate system how we want, so let's make the axis of chopping / axis of rotation the x-axis and the xy plane to be the plane that contains the planar current loop as drawn in the diagram. So let's remind ourselves what the overall goal is. We want to show that the total torque depends only on the area of the loop and not actually on the shape, meaning, for example, a square current loop and a circular current loop and a triangular current loop, all with equal area, have the same amount of total torque. The total amount of torque is the total sum of moments of force times distance from axis of rotation, and we argued that by symmetry of torque couples that there is equal contribution to overall torque from both chopped pieces of the loop. Therefore, right now, we want to show that the total sum of moments of force times distance from axis of rotation on a particular chopped piece is, indeed, in fact, the area of the chopped piece. The magnetic field lines will be contained inside the xy plane which contains the current loop. However, since we don't actually know where the axis of rotation / axis of chopping is, we do not know the relative angle with respect to the x-axis or the y-axis the magnetic field lines make. I will later prove that, in fact, this relative angle does not actually affect the total contribution to torque from this piece of the chopped loop, and we do not actually need to know this relative angle. So for now, let's assume that the magnetic field lines point in the plus y direction, so our magnetic field is IBJ, where j is the unit vector in the plus y direction. To calculate this particular piece of chopped loop's total torque contribution, we'll divide the curve up into infinitesimally small current line element segments of equal length. The total torque contribution is the sum of the force times distance to axis of rotation moments, so each current line element segment contributes a particular moment and the overall sum of moments for the total torque contribution from this particular piece of chopped loop. So if we look at one current line element segment, its moment will be the distance to the x-axis, which is the y-coordinate of the current line element segment's location, times the force on that line segment from the Lorentz force law, which will be the cross product of the current line element segment and the magnetic field IBJ. Since all current line element segments are confined to the xy plane, using geometric and algebraic reasoning shown above, this cross product can instead be mathematically equivalently interpreted as the dot product with the magnetic field IBI, where I is the unit vector in the plus x direction. Now that we've transformed this sum of moments into a dot product, we can interpret this summation as a line integral along the current curve along vector field YIBI. Since we chopped up the original current loop into two parts, right now this part of the chopped loop will not be a closed loop as a result of our chopping. That's okay though, we can fix that. No matter what, the indicated endpoints must be connected to the axis of chopping / axis of rotation, otherwise our long knife used for chopping the loop would not have fully chopped the loop, or the axis of rotation would not intersect the loop, and thus the axis of rotation would be completely outside the rigid body, causing the loop to have overall movement in addition to rotation, or unless our loop is not connected, any of which violates all our previously made original assumptions. Without changing the total net contribution to torque, we can validly draw a current line along the x-axis to connect the two endpoints as demonstrated. This connection contributes 0 to the total torque calculation because the distance to the axis of rotation is 0 anywhere we draw this line along the x-axis, meaning the moment of force times distance to the axis of rotation is 0 along the x-axis of rotation. We originally had a line integral over the vector field YIBI, but with this newly created connection, our calculation of contribution to torque will indeed be a closed-loop line integral over the vector field YIBI. In fact, notice how the curl of the vector field YIBI is negative IBK, where k is the unit vector in the plus z direction. That means we can use Green's theorem or Stokes' theorem to transform this closed-loop line integral into a closed-loop surface area flux integral over the vector field negative IBK. Since the flux integral vector field in the z direction is always perpendicular to the xy plane, that means the surface area flux integral will be IB times the area of the closed loop. Thus, this particular chopped section of the loop will contribute I times B times area of the chopped section to the total torque. By exact same geometric reasoning using line integrals and Stokes' theorem, the other chopped section will also contribute I times B times area of the other chopped section to the total torque. By symmetry of torque-force couples, that means both chopped sections of the current loop must have the same area, and thus the total torque on the current loop is indeed I times B times total area of the loop. However, our proof is not yet complete because we assumed that the magnetic field was pointing in the plus y direction. What if the magnetic field were pointing in a different direction but still in the xy plane? To deal with this, let's go back a few steps. Remember previously to set up our total torque contribution calculation by summing up all the current line elements, segments, moments of force times distance to axis of rotation. So if we look at one current line element segment in particular, its moment will be the distance to the x-axis, which is the y-coordinate of the location of the current line element segment, times the force on that line segment from the Lorentz force law, which will be the cross product of the current line element segment and the magnetic field I times b times cosine theta j minus I times b times sine theta I. Since all current line element segments are confined to the xy plane using geometric and algebraic reasoning shown above, this cross product can instead be mathematically equivalently interpreted as the dot product with the magnetic field I times b times cosine theta I plus I times b times sine theta j, where I is the unit vector in the plus x direction and j is the unit vector in the plus y direction. This is similar to what we did previously. Thus, our torque contribution calculation becomes a line integral along the vector field yib cos theta I plus yib sine theta j. Now, of course, using our previous reasoning, we close our loop by connecting the endpoints on the x-axis as previously demonstrated. Even though we have a different magnetic field now, the connections made on the x-axis have zero distance from axis of rotation and thus contribute nothing to the total torque, thus not affecting our overall calculation. Our total torque contribution calculation becomes a closed loop line integral over the vector field yib cos theta I plus yib sine theta j. Notice how this new vector field is exactly the same as our previous vector field, but rotated by some angle theta. When theta is 0, we have the exact same situation as what we did previously. Remember what we did previously, we showed that any closed loop line integral over the vector field y times I times b times I hat was indeed I times b times area of the closed loop by using Stokes' theorem or Green's theorem. Since area does not change under rotation, we could obviously rotate our closed loop by any angle and get the same result. Alternatively, instead of rotating our closed loop with respect to our vector field, we could rather instead rotate the vector field with respect to our closed loop and get the same mathematical or geometric result. And aha, notice how our new vector field yib cos theta I plus yib sine theta j is just a rotated version of our previous vector field y times I times b times I by theta degrees. Therefore, by rotational invariance of area, indeed any closed loop integral over the vector field y times I times b times cos theta I hat plus y times I times b times sine theta j hat will be I times b times area of the closed loop. Therefore, we have fully proven that the total amount of torque on any planar uniform current loop with uniform magnetic field within the same plane of the loop is indeed I times b times area of the loop, which only depends on the area of the loop and does not depend on the specific shape of the loop. It is also important to consider the direction of the torque induced on the current loop. We will show that the torque vector on the current loop indeed points perpendicular to the magnetic field and is contained within the plane of the planar current loop. The intersection of two planes is indeed a unique line in a particular direction. Previously, we assumed we did not know where the axis of rotation was, but it is easy to show that the axis of rotation cannot be parallel to the magnetic field lines. Let's say our axis of rotation is indeed parallel to the magnetic field lines. Similar to our previous analysis procedure, we can chop up our loop into two pieces along the axis of rotation. Let's examine one particular piece of the two pieces of chopped loop. Let's calculate the total Lorentz force acting on this loop. To do this, we sum up all the forces on each current line element segment of the loop. Let's set up a coordinate system real quick. Moving up vertically on the screen is the plus y-axis, and moving right horizontally on the screen is the plus x-axis, and the uniform magnetic field is pointing in the plus y direction. Using the Lorentz force law on a particular current line element segment, the force on that line element segment is the cross product of the current line element segment with the magnetic field vector I times b times j. Considering all vectors are contained within the xy plane, by geometry and algebra shown above, same as what we did previously, we can convert the cross product into an equivalent value dot product with the vector field I times b times I. Now, when we sum up all the forces on every current line element segment, we get a line integral along the vector field I times b times I. Remember, this is a conservative vector field, and with a scalar field potential I times b times x, and thus any line integral or work done will be just the same difference of potentials of the start and end coordinates, just like with gravitational fields. Considering we chopped our loop along the plus y-axis, and using our previous reasoning, our chopped loop section must touch the chopping axis at both the start and end points of the chopped loop's curve. Considering both the start points and end points of the chopped loop for the line integral have the same x-coordinate, and considering the difference of potentials of the start point and end point only depends on the x-coordinate, that means the difference of potentials of the start point and end point will be 0, and thus our line integral calculation ends up being 0, indicating that there is no net force on the piece of chopped loop that we examined. By symmetry, there is also no net force on the other piece of chopped loop. That means there is no force imbalance across this particular axis of rotation where we put the knife to chop the loop into two pieces. And thus, there is no torque in this direction. This geometrically holds true for chopping the loop up into two pieces with the knife along any axis of rotation that is at least parallel to the y-axis. That means all of the torque or all of the force imbalance must be in the perpendicular direction. If we chop the loop along an axis of rotation parallel to the x-axis, we should have the most force imbalance between the two pieces of chopped loop, and thus the most torque. Mathematically, this holds true, because indeed, if we chop up our loop into two pieces along the x-axis, and considering the total force on each section of chopped loop only depends on the x-direction distance between the start and end points of the section of chopped loop, by geometry, there is indeed the maximal and non-zero force imbalance shown in the diagram. This orientation of chopping the loop into two pieces along the x-axis by visual geometry creates the maximal x distance between the start and end points of the section of chopped loop, creating the highest torque force imbalance that is non-zero. So in conclusion, if we have an xy planar loop of current with a uniform magnetic field pointing in the plus y direction, the total torque vector on the loop will be I times b times area of the loop, pointing along the plus or minus x direction depending on whether we have a clockwise or counterclockwise current, which in this case is the cross product of the perpendicular to plane normal to area vector scaled by current and the uniform magnetic field vector. What if our uniform B magnetic field is not actually contained to the xy plane? Well, if the B magnetic field has a component along the z direction, that will not contribute to the translational movement or torque, and thus only the uniform B magnetic field component along the xy plane of the current loop contributes to overall torque. This geometrically and algebraically holds true for the cross product operation by Cavalieri's principle. But we need to prove this property holds for the xy plane current loop with a z-oriented magnetic field so that we will be mathematically actually allowed to use the cross product in the future for any physical scenario. By linearity of vector summation / integration / cross product / dot product operators, we can treat the magnetic B field xy plane torque contribution separately from the magnetic B field z direction torque contribution, because any uniform magnetic B field orientation can be treated as the sum of multiple vectors, the xy components and the z components. So, if we have a current loop in the xy plane subjugated to a uniform magnetic field in the z direction, what is the total force on the loop? The force on any particular current line element segment is the cross product of the current line element segment, which is contained in the xy plane, with the magnetic field IB k hat, where k hat is unit vector in the z direction. If each infinitesimal line element segment vector has same length, that means the force on each infinitesimal current line element segment is equal in magnitude for each segment and perpendicular to each segment, and thus the force vector on each equal length current line element segment is essentially just a transformation of each infinitesimal equal length current line element segment vector, scale by I times b in magnitude, and rotate by 90 degrees. This is easily visualized similarly to the unit normal vector to the curve of the current loop as drawn in the diagram above. By stacking up or lining up the set of all the infinitesimal line element segment vectors end-to-end head to tail in order, we get the original curve of the entire loop. If we sum up or follow along the infinitesimal line element segment vectors, it is visually represented as if you took baby steps to walk along or follow the curved path of the loop. And since it is a closed loop, you will eventually end up right back to where you originally started. So the sum of all the infinitesimal line element segment vectors is 0, and it is the same with the force vectors. Note that by geometry, all the force vectors are contained in the xy plane, and there is no force anywhere pulling in the z direction. Right now, the force vectors are the scaled unit normal vectors of this loop and are not connected. What if we stack up or line up the set of all the force vectors end-to-end, head-to-tail, and in order, just like the corresponding line element segment vectors? Considering each force vector corresponds to a 90-degree rotation and a scaling by I times b of the corresponding current line element segment, we will get the original curve with same proportions but dilated or enlarged by a factor of IB and of course rotated by 90 degrees, which overall still represents a closed curve. And thus, if we sum up all of the forces acting on the loop, we will get 0 because summing up or following all of the forces is visually interpreted as taking baby steps to walk along and follow the curved path of the closed loop, which will end up back where it started eventually. Therefore, the total force acting on the loop is indeed 0, and the loop will not undergo translational movement. If we have a current loop in the xy plane subjugated to a uniform magnetic field in the z direction, is there any torque on the loop? This is an interesting question. Though we know there is no force anywhere in the z direction, so no corresponding torque to flip the loop like a pancake in a pan, so to say, but we haven't yet disproven the possibility of rotational torque forces in the xy plane to, so to say, rotate the pancake in the pan. You probably know the drill by now. To show that there is no torque, we want to set up some sort of line integral. Without loss of generality, let's set our planar current loop curve in the xy plane and set the origin to be the unique center of rotation, which is the center which the pancake rotates around in the pan. Now let's look at the geometry of this situation. We want to take some sort of line integral along the original current loop, and that line integral needs to be the sum of the moments of distance vector to center of rotation times force perpendicular to that distance vector. The force is always perpendicular to the current line element segment, and thus by 90-degree rotation by visually looking at the geometry and algebraic reasoning above. Instead, we should sum the moments of distance vector to center of rotation times current line element segment parallel to the distance vector, and then all linearly scaled by factor IB accordingly. Now, the parallel component can be represented as a dot product with the distance vector. The distance vector can be represented as a vector field x times I hat plus y times j hat. Notice how we've now finally converted our torque calculation to a closed-loop line integral along the vector field xi hat plus yj hat. Notice how this particular vector field has zero curl, and thus by Green's theorem or Stokes' theorem, this closed-loop line integral will be 0. Additionally, this vector field can be written as the gradient of scalar potential field xy, and thus by the gradient theorem or fundamental theorem of multivariable calculus, a closed-loop line integral will be 0. Therefore, we have proven that there is no torque on a xy planar loop of current from a magnetic field in the z direction. It is worth mentioning that this previous reasoning follows physical intuition. If we have a balloon of any shape filled with some amount of air, the force vectors of the air inside pushing out on the surface of the balloon will not only be parallel to the normal vectors of the surface, but additionally each force vector will be the same magnitude considering pressure is uniformly distributed over the surface. If we inflate a balloon, it increases the surface pressure, causing the balloon to expand, but from physical observation the balloon does not rotate. Likewise, using our previous mathematical justification, we have mathematically shown that an inflated balloon will not rotate no matter what shape the balloon is currently in. Therefore, after all this mathematical and physical reasoning, we have fully derived and proven the cross-product formula for the torque on a planar loop in a uniform magnetic field in any orientation in 3D space. So moving forward, what does this mean? So from the Biot-Savart law, we know that a planar current loop of any shape creates a magnetic field in the center. It was assumed that any magnetic field in the universe comes from some sort of current loop, which is the Ampérian loop model of magnetic fields. Indeed, the torque on any planar Ampérian loop only depends on the strength of the uniform magnetic field perpendicular to the normal vector of the planar Ampérian current loop, the amount of current going through and around the Ampérian current loop, and the area of the Ampérian current loop, regardless of the shape of the Ampérian current loop. Previously in part 3, we had a hand-wavy justification of this expression by simply making the physical observation of the natural world that north poles attract south poles and vice versa. This reasoning is not grounded on any of the fundamental axioms of electromagnetic theory. However, in part 3.5, we used the Lorentz force law, which is indeed included in the list of electromagnetic axioms, to fully mathematically prove this equation for the Ampérian loop model of magnetic fields. An electron can be classically modeled as a spinning solid sphere of charge or a spinning hollow spherical shell of charge. Notice how both scenarios can be interpreted as a superposition of concentric planar circular Ampérian current loops. By visual inspection of the diagram, by geometric cylindrical symmetry about the axis of rotation indicated in the diagram, the torques from each concentric circular current loop never cancel each other out, and they all add up linearly in the superposition for the total torque on the solid or hollow sphere rigid body. Therefore, an electron or proton in a uniform magnetic field will undergo some measurable amount of torque force based off of some sort of Amperian current loop with some sort of current which is consistent with our Amperian loop model. So as far as the torque is concerned, it's almost as if we squashed or squeezed or flattened out and squeezed in the electron/proton into a plane perpendicular to the axis of rotation to form some planar Amperian current loop. And though most magnetic fields are not uniform, the electron is so tiny and localized that the magnetic field going through the electron/proton is more or less the same and approximately uniform. At the end of the day, this means that our previously derived cross-product formula for the torque on a planar current loop in a uniform magnetic field in 3D space indeed should hold for an electron or proton. So mathematicians like to think of crazy exceptions to anything and everything and will question any idea you have to the extreme. So the proof of the cross-product torque formula for a planar current loop breaks down if we have a self-intersecting loop, Green's theorem and Stokes' theorem breaks down. At this point, it is better to examine them as multiple connected loops though. It is possible to mathematically construct a connected current loop with infinite area, and this makes no physical sense. It is possible to mathematically construct a connected current loop with non-measurable or undefined area, which also does not make physical sense. Examples of this would be the indicator of the rationals/Vitali set, or the indicator of the Cantor set, with vertical connections, of course, to close the loop. That means, given the rules of mathematics, we get multiple logically equally valid but numerically contradictory area value measurements for the loop. Considering torque only depends on area, I suppose this situation remains mathematically valid. It is possible to mathematically construct a connected current loop with finite area but infinite length, but this also makes no physical sense. Some examples of such crazy geometric objects are the Dirac delta function, any loop which doesn't have compact support, but whose cross-section length decays faster than order 1 over n, such as Torricelli's trumpet or Gabriel's horn, or Pareto distribution or normal Gaussian distribution, the Koch snowflake, Sierpinski gasket triangle, other objects with non-integer Hausdorff dimension or Hausdorff measure, just about anything jaggedy or fuzzy enough that exhibits the coastline paradox. It is also mathematically possible to construct a connected current loop that is a space-filling curve, such as the Peano curve or Hilbert curve. Not only do these have infinite length in order to have enough stuff or mass to completely fill space, but it's also really hard to know what's really going on with their area. This, of course, makes absolutely no physical sense in the real world. It is also mathematically possible to construct a current loop curve that is so topologically weird that it doesn't represent anything in the real world, such as the topologist sine curve as shown. There's a joke that demonstrates how differently mathematicians think. An engineer, a physicist, and a mathematician are all tasked with applying their knowledge to build a fence enclosure for a herd of sheep to keep them from wandering or grazing too far away from the herd sheepdog. Not sure why, though, since unbiased binary random walks, like a drunk person wandering in 1 or 2 dimensions, will always eventually find their way to return home, which is not the case for an unbiased binary 3D random walk for herding birds, which mathematically might fly away and get lost forever, if not for their good navigation skills, but sheep are luckily confined to 2-dimensional grassy pastures. Anyway, the one who builds the best fence for the sheep gets a delicious mutton dinner on the house or farmhouse. The engineer, being the most practically minded, quickly builds a simple square fence around the sheep to get the job done as efficiently and conveniently as possible. The physicist, becoming competitive, says, "I can do better," and he bends the fencing material into a circle to get the most grazing area for the least usage of fence material, which is the most economical for the farm funds. The mathematician, on the other hand, completely ignoring the attempts of the other two and all practical considerations, builds a tiny little fencing enclosure around himself and says, "I define myself as outside." This indeed does technically get the job done of keeping all the sheep together on the inside of the fencing enclosure, which is truly separated from the outside world, all while using the absolute least amount of fencing material. The mathematician enjoys a nice mutton steak dinner before all the sheep run away. This joke, along with the perverse examples of current loops, provide a general picture of sort of what pure mathematicians think about and just how drastically different the goals of mathematics is from those of science and engineering. It portrays just how far removed from the real world the field of pure mathematics can be, which is interesting and amusing to mention in this extremely interdisciplinary series. We certainly could have been satisfied earlier with just being given the magnetic moment cross-product formula for torque on a planar current loop in a uniform magnetic field, and simply accepting this relation as intuitive logical truth without further question, even if it is an incomplete explanation. If one did skip this optional part 3.5, one would miss out on the illuminating insight that one acquires by comprehending something at its very core or essence or detailed fundamental level from the ground up. Hopefully this detailed derivation and proof of the aforementioned formula satisfactorily fills in any missing holes from the discussion on magnetic resonance. Many concepts from math were applied in the analysis of this physical scenario, which goes to show just how useful math can be in the real world and also show the extent of how diverse the applications of math can be. Thus concludes part 3.5, the mathematics of magnetic resonance.